They're old. So just check it. There's another one that almost out of class here. Right. Okay, so I think last time we spoke a fair amount about the Cramer-Rao bound, and I want to sort of complete that discussion today. We sort of covered the very basics, and there's some other aspects to it that are equally important. So let me just start by reviewing it. So the Cramer-Rao lower bound, we said the following: you have data x and a parameter theta that you're interested in, which the data gives you some information about. So given that the following regularity condition is satisfied, this is true, and this P is conditional density of the joint conditional density of x given theta. Then, for any estimator, theta hat equals g of x, which is unbiased. We have the variance of theta hat is lower bounded by 1 over the Fisher information. And if you remember, the Fisher information had two different definitions. So this I of theta could be written as minus the expected value of the second derivative of this log likelihood function. And it's also possible to write this as this first derivative squared expected value. And if you remember, this thing here was called the score function. And the score function has zero mean, that's this condition. And this really is, another way to think about it is it's the variance of the score function. Okay, that's the information. Okay? All right, so this is the summary from last time. Now, sort of part 2 of the Cramer-Rao bound theorem gives you an idea of how you might go about finding an estimator that in fact achieves the Cramer-Rao bound. So part 2 is the following. Furthermore, if and only if, so we write IFF, if and only if, this log likelihood function can be decomposed as follows. I of theta times some function g of x minus theta. Okay. if the derivative of the log likelihood, if this the score function can be written like this, then theta hat equals g of x is an unbiased estimator with variance 1 over I of theta. Okay, what does that mean? It means theta hat equals g of x achieves the Cramer-Rao lower bound. Okay? There's a name for this. So this is now going to be basically your minimum variance unbiased estimator. Okay? And this idea is also called efficiency. Okay? So if you manage to come up with an estimator that in fact achieves the bound, then you have this concept of efficiency. Now, this is something that one has to be a little bit careful about. I'll say more about this later. But efficiency assumes that the Cramer-Rao bound is achieved for every value of the unknown parameter. So if I go back for a second and look at what I wrote here, this bound actually depends on the different values of theta. So if you have an estimator that achieves this bound for just one value of theta or a few values of theta, it's not called efficient. I think you asked me about this at the end of that last class, right? So, but if it achieves the bound for every value of theta, then we call it efficient. Okay. As we'll see, there are other related concepts. For instance, it's possible for an estimator to achieve this bound asymptotically, which means if you have an infinite amount of data, you might achieve this bound. That's called asymptotic efficiency. Okay, so we'll get to that a little bit later. But for now, let me kind of try to explain this and how this all works and prove to you that in fact, if you can do this, then this estimator is in fact unbiased and that in fact it achieves this particular variance. So that this is not such a mystery. Okay, so let's start again with the regularity condition. Okay, so this is the expected value okay, this is equal to 0. And we can write this as the integral with x given theta, d theta, dx given theta, dx. Okay, this is equal to 0. So I'm just reminding you this by way of what we did last time. Okay. All right. Okay. So now let's see if this is true, and we know that this is true. Now, if this thing inside the expected value is in fact equal to this, then I can write the expected value of this I of theta times g of x minus theta is equal to 0, right? And of course this immediately implies that theta hat is equal to g of x is unbiased, right? Okay, so what this is this clear, or do we need to take some steps here? I'm happy to do it. Looks like I need to take some steps. Okay. All right. So we multiply this guy through, and what we come up with is the following. So I of theta times expected value of g of x minus theta times I of theta is equal to 0. Okay? So this is fine, right? Okay. All right, so what this means is, if I can factor an I of theta from this, is expected value of g of x minus theta is equal to 0. Presumably this part is not equal to 0. This is the Fisher information, so this has to be 0. Okay? So theta is equal to expected value of g of x, which is theta hat. Okay, so this means that the estimator is unbiased. Okay? Is that a little more clear? So g of x is theta. Theta hat. Okay, so that part we've got. What about the variance? So what about the variance of theta hat, which is variance of g of x? This is what? Okay. So once again, let's take the condition. I of theta g of x minus theta. Okay, and what we're going to do is compute the variance of both sides of this expression. Okay? Variance of d by d theta. Okay, so if you remember the variance of this guy, this is the expected value of this derivative squared, okay, which is in fact related to the Fisher information, right? Okay, so what do we get from this? Okay, so I'm just looking at the variance of the left-hand side. So variance of the left-hand side, is I of theta, right? So this is the definition of the Fisher information. Okay, what about the variance of the right-hand side? That's the variance of this guy here. Okay, so that's the variance I of theta times g of x minus theta. Okay, so this becomes I squared theta times the expected value of g of x minus theta squared. It's this because this guy here is zero mean, right? Because the estimator was unbiased. Okay? And what is this? This is simply I squared theta times the variance of g of x. And another way to write this is this is I squared theta times the variance of theta hat. Right? Okay, so this is the variance of the right-hand side. This is the variance of the left-hand side. So they have to be equal. So variance of theta hat is 1 over I of theta. Okay? So we proved what we set out to show. Okay, so you get a an unbiased, minimum variance unbiased estimate. Okay, any questions about that? Now, the second part of the Cramer-Rao bound theorem is just as important as the first part, because it gives you a mechanism for either finding a minimum variance unbiased estimator or somehow showing that it doesn't exist. Okay? In other words, if you can go back and look at this expression, if you can write this left-hand side as this, then you've got your answer. This is your estimator, and this is the variance of the estimator, 1 over the variance of the estimator. If you can prove that this left-hand side cannot be written like this, then what you've done is you've proved that there is no minimum variance unbiased estimator. Okay? It's quite useful. All right. So now let's do a few examples to see how these bounds actually work for us. Let's do again the simple problem that we've been carrying around with us. X of n is a plus wn. A is unknown, w is normal, zero mean variance, sigma squared, and it's IID. Okay? So the distribution of x of n is a Gaussian. If you have n IID densities, n IID samples from the same density, then the joint distribution is the product of the individual distribution. So I'm not going to go through all those details. We've done those many times up to now. So I'm just going to write this. dA is equal to 1 over sigma squared, the sum n equals 1 to n, and that's how many data points I'm assuming I have. X of n minus a. Okay? All right, so this is what this score function looks like. And now I'm interested to see if I can write this score function in this fashion. Okay. It turns out in this particular case, it's really not very hard to do. It's just a matter of kind of manipulating the terms a little bit. So I'm going to rewrite this as n over sigma squared times 1 over n sum n equals 1 to n x of n minus a. Okay? So now if you look at this, I've isolated the parameter here by itself. That's theta. This is only a function of the data. This is g of x. Okay? And it turns out this is in fact the Fisher information. Okay? So indeed, we have a minimum variance unbiased estimator in this case for a hat, and it is the average. Okay? And of course you can verify this if you like. If you in fact compute the Fisher information, you can take the second derivative, take the expected value of that, and what you get is n over sigma squared, which is exactly what we had here. Okay, so the Cramer-Rao lower bound, just in its generic form, would be the variance of a hat is bigger than or equal to sigma squared over n. But in this case, here, the variance of a hat is in fact equal to sigma squared divided by n. So what you've done is you've achieved this lower bound. Okay? So what that means is that this is an efficient estimator. Okay? So what you've also seen is that this variance, this lower bound also doesn't depend on the value of the parameter that you're after. It doesn't depend on A in this case. That's generally not true. In other words, the lower bound will generally depend on the actual unknown parameter. Okay, we just got lucky here because the problem is so simple. So don't be deceived by that. Okay, let me just draw you a picture for a moment to give you an idea of what, in general, these problems will look like. So let's say, we take this axis theta, and say we take this axis here to be the variance of theta hat. Okay. So let's consider all these unbiased estimators. Okay. If I were to compute this Cramer-Rao bound, the right-hand side, the lower bound, what I might get is, let's say I might get a function that looks like this. Okay, I'm just drawing something arbitrary. So what this shows me is the minimum achievable, minimum variance, maybe achievable, maybe not, for that particular estimate. Regardless of what algorithm you use, regardless of what estimator you use, your variance will never go below this red line for any of these values of theta. Now, if you go ahead and you pick a particular estimator and you compute its variance and you plot it as a function of different values of the underlying parameter, you're going to get different looking curves. So for instance, you might get one estimator that might have a variance that looks like this. Okay, so this might be estimator 1. You might have another estimator that behaves completely differently. Maybe it goes like this and it does that. That's estimator 2. Okay, and so on. Any one of us can come up with an estimator, and they might have different properties. In fact, we might be lucky enough that this guy might in fact touch here. Okay? That does not make this estimator efficient. And that's what I just said. What makes this efficient is the black curve was right on top of the red curve. That would be efficiency. Okay? Okay, now let's go to a somewhat more complicated scenario. Let's say now we have data, a signal is measured with noise plus W of n. Let's say this W of n is again Gaussian zero mean variance sigma squared, and we have n data points. So what this is, it's some function. I know what the function is, but I don't know the parameter inside the function. So for instance, S of n could be cosine of omega t, okay? And the parameter that's unknown could be omega, could be the frequency of that cosine. Okay, so I know the form of the function, but I don't know the actual parameter value. And I got these measurements and I want to estimate them. Okay, so again, we write the joint PDF. And what we get is the following. So 1 over 2 pi sigma squared to the n over 2 times exponential minus 1 over 2 sigma squared sum sub n minus s and theta squared. Okay, so we take, now what I want to do is, again, compute the Cramer-Rao bound for this problem. I want to see how difficult it is to estimate this parameter theta. So you take the derivative, second derivative, and what you get is 1 over sigma squared sum plus 1 to n x of n minus s and theta. Okay, this is a bracket. So this, all of these terms are a function of n, so everything is getting summed over n. Okay. Then we take an expected value minus the expected value of this second derivative. Okay, and when you do that, what you'll see is that this term will drop out. Okay, because the expected value of this guy, basically expected value of x cancels s, and so this term will go away. And so what you're left with is 1 over sigma squared n equals 1 to n ds d theta squared. So what we learned from this is that the variance theta hat is lower bounded by sigma squared divided by the sum n equals 1 to capital N of ds d theta squared. Okay, so let's see what this tells us. This right-hand side tells us a couple of things. First of all, the more noise you have, the larger the variance of the estimate will get. That part is obvious. Second, the more data points you have, the larger the denominator will get, so your variance could be smaller. Okay? So that's point number 2. And finally, what you see is that in the denominator, the things that you're adding are derivatives of the function s with respect to theta. Okay, what does that mean? What this is doing, again, is measuring the sensitivity of your function to changes in values of theta. Okay? So let's consider, for instance, if this denominator, if these derivatives, for a particular value of theta that you're interested in, if this derivative was 0, what would happen? The denominator would basically make this whole thing blow up, right? And what that would mean is that the variance of theta hat would become infinity. It would be lower bounded by infinity, which would mean that it's impossible to estimate theta. So let me summarize. If the function is not sensitive at all to the value of the theta, in the sense that this derivative is 0, then you can't estimate the parameter. Which means that the data is giving you no information about the parameter of interest. On the other hand, if the parameter of interest makes the derivative of this jump at that point, then this right-hand side would become small, which would mean that the parameter is easier to estimate. Yeah?
Can you do this with integral transforms?
What does that mean?
Say, take the Fourier transform of your known S. Take the Fourier transform of your known S, and with respect to whatever your parameter is, then take the Fourier transform of your signal with respect to whatever your unknown parameter is, and then correlate the two transform functions in the new domain and extract the parameter that way.
Are you talking about computing the bound or estimating the parameter? I'm a little unclear as to what you mean.
I guess estimating the parameter.
Well, yeah, we're not really talking about estimating the parameter here, though. We're just talking about calculating the bound. Okay? So what you can do, what you certainly can do, is this thing here can be computed in the Fourier domain, if that's what you're asking.
Yeah.
So you can take the signal S. If you know what the signal S looks like, you can compute this quantity in the Fourier domain and look at how big it is across different frequencies. And that'll be kind of equivalent to looking at this in the actual time domain. Okay, so you can do that. But I'm not talking about estimating the parameter yet.
Then is there a way to do this in the frequency domain?
Do what? Do this calculation?
Yes. Get the variance of the estimation.
Well, yeah, I mean, this right-hand side can always be calculated in the Fourier domain. So, yeah, you can do that.
But would that involve doing the Fourier transform after you've gotten to this point, or can you start at an earlier point?
Well, what you have to do is remember that these quantities, let's see. You can do it in the Fourier domain from the beginning, but there's really no advantage in doing that because it doesn't make life any easier in general. But if you look at something like this, for example, right, everything here in the computing the lower bound is all about computing either this derivative or this derivative and then taking an expected value, right? So if you look at this, the expected value of this square is the variance, right? It's the integral of the square of this term times p and so on. And so that's an energy calculation, right? Just like anything else, you can compute the energy in the pixel domain, or in one domain or in a transform domain. So yeah, you could do all of these things in the Fourier domain if you wanted to, but the way it's written here, there's really no compelling reason to do that.
Okay.
Okay, so what I've done here is these examples that we showed and the results that we showed were mostly for the scalar case. I also want to give you the general vector case for the Cramer-Rao bound. So So vector Cramer-Rao lower bound. So here, what we mean is that instead of a single parameter theta, you have a vector, theta 1 through theta, let's say p. So p is, little p here is the number of parameters you're trying to estimate. Okay, and so accordingly, theta hat would be theta 1 hat through theta hat, theta p hat. Okay, and notation-wise, expected value of theta hat is, of course, the element-wise expected value. And the covariance of theta hat is now going to be a P by P matrix. Along the diagonals of this matrix are going to be the variances of the individual terms. Variance of theta 1, variance of theta p hat. And along the off-diagonal terms, I'm just going to show you what one of them would be. Let's say in this position, let's say this is the ith row and the jth column. Okay, this guy would be the covariance of theta I hat, theta j hat. Okay? Just by way of setting it up definition-wise. Okay, now, in this case, for the vector case, the regularity condition is the same as before, except that the derivative is now a gradient that you're computing with respect to a vector. So it looks like this. The expected value, derivative log p of x given theta, d theta equals 0. This is the regularity condition. This derivative is now a derivative with respect to a vector, right? So you can actually write this as the gradient of the log likelihood function with respect to theta. Okay, so the Fisher information in this case is going to be a matrix. I of theta is going to be, this is the Fisher information matrix, and what it's going to be, I'm going to write down for you, it's I jth element. Okay, it's going to be minus the expected value log of p x given theta, d theta I, d theta j. Okay? So you basically differentiate both with respect to theta I and theta j, and the minus an expected value, and that gives you the ijth element of the Fisher information matrix. So this just means this is the ijth element of the p by p matrix in this case. Okay, now there's something slightly delicate about this. What happens is we write the Fisher information matrix like this. Covariance of theta hat is less than or equal to I inverse of theta. Okay, so this is the Cramer-Rao bound for the vector case, but I have to explain to you what it means. This is the CRLB for the vector case. This inequality does not mean that the elements of this matrix are bigger than the elements of this matrix. Okay? What it does mean is that the difference between these two matrices is positive definite. This is a big deal. Okay? It's a very important difference. So this is bigger than in a matrix sense. So let me write this clearly. This covariance of theta hat minus, bigger than or equal to I inverse theta means that the covariance of theta hat minus I inverse of theta is positive semi-definite. Well, it's symmetric. We know that it's symmetric. So this difference means that it has real eigenvalues. Positive semi-definite means it has real eigenvalues that are positive or 0. Okay, non-negative. Now, what if you are only interested in writing down the Cramer-Rao bound for just one of the elements in that vector that you're trying to estimate? Well, what if you want this? You want the variance of theta I hat, just one of them. Well, this would be, you compute the inverse of the Fisher information matrix, then you pick its ith element. Okay?
Can you show the last slide?
Here?
Yeah.
So in other words, if this theta is a vector, and you're interested in just the variance for one of the components of that vector, the bound for that is given by first inverting the Fisher information matrix, then going to the ith element, or the ith element along the diagonal, and this is the proper way to think about the Cramer-Rao bound. Okay, so this would be the CRLB for that particular parameter. Now you might want to do something a little more lazy, which is, what if I just did this? Okay? What if I just did that? Would that be a bound? In other words, I take the ith element of the Fisher information matrix. I don't invert it. I don't invert the matrix. I just take the ith element of the matrix itself and I just do 1 over it. Well, it turns out this is also a valid bound, but it's weaker than the Cramer-Rao bound.
It's diagonal.
Pardon me?
If it's diagonal,
Yeah, if it's diagonal, then it's fine. Yeah, one and the same, right? So here, this is a weaker bound. Okay? It's sometimes useful, even to have that weaker bound, but you can't call it the Cramer-Rao bound anymore for that particular parameter. Okay, what about the general case where you have, so this is, I gave you this is the Cramer-Rao bound for the unbiased case. For the biased case, what we can do is basically put everything together, and the formulation for that is you look at the vector mean squared error as a function of theta, and this is what I wrote as expected value of theta hat minus theta times theta hat minus theta transpose. Okay? And it turns out that this is less than or equal to, in the sense that we just talked about, in the positive definite sense, less than or equal to this. Expected value of theta hat, d theta, I inverse theta, d e theta, d theta transpose, plus d of theta, b transpose theta. Okay, so if you look at this equation on the right-hand side, you get the bound at the right-hand side. It looks very much like the scalar case. In the scalar case, we had the Fisher information in the denominator, and we had the square of the derivative of, this is a hat here, the square of the derivative in the numerator, and then we had bb transpose, or b squared added. Bottom line is that when you have a biased estimator, your lower bound on the mean squared error now depends not only on the Fisher information matrix, but also on the bias and the derivative of the bias. Okay? So this, I don't know if I mentioned this last time, but this is actually kind of an interesting thing, because if you happen to know that your estimator has a bias that is constant, right, then this part doesn't matter, right? Because then what happens is dE theta hat by d theta this term is a constant. Okay? So oftentimes, if you can study a problem and come up with an estimator that has a bias, but if the bias is constant, you can kind of figure out roughly what it is, you can get rid of it. You can remove the bias, and then you'll have this term go away, and these terms will just become ones. Okay, so you can effectively come up with an unbiased estimator. You can characterize the bound, especially if it's very simple, just a constant or linear bias. Okay, so another example. Any questions? No? Okay, so now let's do this case where two parameters are unknown so that we can see the vector parameter in action. So x of n is a plus wn almost 0 mean sigma squared, and the data is 1 to n, iid again, and the unknowns parameter is theta 1, theta 2, which are the amplitude A and the variance sigma squared. These are the unknowns. Okay? So, I mean, if you really want to think of it a slightly different way, you could just absorb this A into W and think what you're measuring is just noise with mean A and variance sigma squared, both of which are unknown. Okay, so you're making a bunch of measurements and you're trying to find the mean and the variance of a bunch of noise measurements. Okay, so the log likelihood function looks like this. N over 2 log of 2 pi minus N over 2 log of sigma squared minus 2 sigma squared sum x of n minus a squared equals 1 n. Okay? Now we compute the Fisher information matrix, I of theta. This is minus expected value log of p d theta 1 squared minus expected value d log of p d theta 1 d theta 2 minus d theta 2 d theta 1 minus d theta 2 squared. Okay? Yeah?
What is that?
Pardon?
Minus n over 2 ln 2 pi.
Well, this is just a this pi.
Oh, got it.
Okay, so then we take the derivative. So theta 1 is A and theta 2 is the variance. And PDA squared, this is minus n over sigma squared. PDA sigma squared. This is minus 1 over sigma to the 4th times the sum of x of n minus a. Okay? And sigma squared is minus n over 2 sigma to the 4th minus 1 over sigma to the 6th sum x of n minus a. Okay. All right, so if you look at this part here, by the way, I should say that this matrix is symmetric, so even though I wrote these differently, they are exactly the same. These two off-diagonal terms are exactly the same. Okay, I just wrote them d theta 1, d theta 2, d theta 2. It doesn't make any difference. All right, so if we go to this one, we have to take expected values of all of these things, right? So if you take expected value of this guy, what you immediately see is that it's 0, right? So this term, the expected value of this term is 0, so this whole thing just goes away. Okay? And then we compute the expected value of these two other terms. This part also drops out, and what we end up with is the Fisher information matrix. Looks like n over sigma squared, 0, 0, n over 2 sigma to the 4th. Okay? And therefore, the inverse Fisher information matrix is a diagonal matrix, so you just flip the diagonal terms. You get sigma squared over n, 0, 0, 2 sigma to the 4th over n. And what this means is now the variance of a hat is lower bounded by sigma squared over n, and the variance of the estimated sigma squared is lower bounded by 2 sigma to the 4th over n. Okay? Now I was able to do this because this is a diagonal matrix, so the inversion of it was very simple. But there's something also interesting about the fact that this Fisher information matrix has off-diagonal terms that are 0. What that tells you is you can actually estimate these two quantities independently. Right? You can estimate one, then estimate the other. Okay. In other words, the lower bound can be computed separately from these two as well. For these two as well. The other thing you learn here is that if you look at this for the same n, okay, as sigma gets bigger, this one is harder to estimate, right? Because sigma to the 4th grows a lot faster than sigma squared, right? And that's not a surprise, right? I mean, you kind of all know intuitively that if I give you a bunch of random numbers and both the mean and the variance are unknown, the mean is easier to calculate and it's more reliable, right? So that's what this is telling you. Okay? Questions so far? Okay. Okay, so this result that I just wrote down, yeah, this one. This one that I wrote down, the left-hand side is a matrix. So this is what we call the matrix mean squared error, or vector mean squared error, okay? It's not a single scalar, but we can also write down a single scalar version of the Cramer-Rao bound, and the way that is done is the following. So we can take the two cases, biased, so unbiased case. So the standard Cramer-Rao bound says covariance of theta hat is lower bounded by this I inverse, okay? Now, if I want to describe this with a scalar mean squared error, I can write this as the expected value of the norm of theta hat minus theta squared. Okay? So theta here is now a vector. Okay? Now, if I do this, then it turns out all I have to do is basically take trace of both sides of these guys. Because this is, in fact, the trace of this matrix. Okay? So this is equal to the trace of the covariance of theta hat, and that's less than or equal to trace of I inverse theta. Okay? So you take trace of both sides of these, and for the general biased case, then the lower bound involves not just the trace of the covariance, but the trace of the covariance plus the norm of the bias vector squared. So this guy becomes the trace of I inverse theta, I'm sorry, trace of covariance of theta hat plus the norm of B of theta squared. Yeah.
How did you make those sums disappear in the FI matrix?
Which sums?
Um,
Are we going back a couple slides?
I think it was the last slide.
Here?
With the exit. Yes. How did you make that 1 over sigma 6? How did you make that sum?
How this disappear? Well, remember the Fisher information, you have to take expected values of these derivatives, right?
Okay.
So when you take expected values, this term goes away. Okay, so let's write this in a more explicit way. So what this gives us is this expected value of the norm of theta hat minus theta squared. This is equal to the sum of the expected value of theta hat minus theta I hat minus theta squared. Okay? Where I equals 1 to p. Those are the number of parameters that you have. And of course, this is what you basically deal with. This is what you call the mean squared error for each one of those estimators. So in other words, the overall mean squared error for the entire vector, thought of as a single scalar, is the sum of the mean squared errors for each one of the components. Okay? So what you then have is this thing becomes, the lower bound to this becomes the trace of, that's a little bit messy, dB d theta, I inverse I plus dB d theta transpose plus the norm of the bias squared. Okay, so again, it involves the gradient of the bias. Before, in the other expressions, I had written this part here was the derivative of the expected value of theta hat by theta. I've just written it explicitly in terms of the bias here, so you can see how it looks different. So for instance, if the bias is 0, this goes away and that goes away, you have identity on these sides. If the bias is constant with respect to theta, again, you get something very simple. Okay. All right, so there are a few other tricks that are often useful in practice. So again, let me go back to the scalar case. And let's write the variance of theta hat lower bounded by this 1 over I of theta. Okay. Sometimes you might be interested in not theta itself, but some function of theta. And so if you've done all the fancy calculations to find out what the lower bound is for estimating theta, and now I ask you, well, I don't really want theta, I want theta squared, or I want some function of theta, f of theta. What would that be? So let's say alpha is equal to some f of theta. And what I want is actually the variance of alpha hat to be lower bounded by something. How do I do that? Okay. It turns out it's very easy to do. All you have to do is to keep in mind this function and basically compute the derivative of the function. So the variance of alpha hat is lower bounded by df d theta squared divided by the same I of theta as before. Okay? So this derivative is what makes all the difference. So for instance, in the trivial case, if alpha is just theta, then this derivative is just 1. So you get back to what you had before. Okay. This is sometimes useful if you want to just simply compute a linear function of the data. A linear function of the parameter. So let's say your alpha is equal to some constant a theta plus b. Okay, and this a and b are just some fixed constants. Okay, so if we look at this, then df d theta squared is just a squared, right? Okay. Now suppose theta hat is efficient. In other words, suppose you got lucky and you came up with an efficient estimator for estimating this parameter theta hat. What would happen if you now wanted an estimate of this other parameter alpha? Would that also be efficient if you just plugged in theta hat into this equation? But it turns out the answer is yes, if this function is simple. In fact, if the function is linear, like this is more generally called affine, then yes, efficiency is preserved. On the other hand, if the function is anything more complicated, like a general f of theta, efficiency is generally destroyed. Okay, this is again a big deal, because you might have a great estimator achieving the lower bound and all that stuff of theta, but maybe what you really want is theta squared. Well, not efficient anymore, not generally. Okay, and this is easy to see because if theta hat is efficient, then the variance of theta hat achieves the bounds, which means this is equal to 1 over minus the expected value of this log p d theta squared. Okay, and now you just have to ask yourself, what is the variance of alpha hat? This is the variance of a theta hat plus b, okay, which is a squared times the variance of theta hat, right? Well, you just got that, right? So the efficiency is preserved. So the variance of variance of alpha hat is in fact equal to a squared times this quantity, which achieved the lower bound. So this is a very simple case, and for that case efficiency is preserved. Most of the time, however, it is not. Okay, let me give you an example. See, x of n is a plus wn. Okay, so we know that this a hat, 1 over n sum of x of n, we know that this is efficient. Right, I showed it to you in an example just a little while ago. What if I, instead of a, I want to estimate a squared? What about a squared? A squared. Okay. Suppose I do a squared like this. I say a squared hat is 1 over n sum x of n, and then this whole thing squared. Okay. I just take this guy and plug it in here and square it and say that's my estimator. What happens here? Well, let's take a look at the expected value of this estimator. I'm not going to take you through all the calculations, but I'll show you that this is a squared plus sigma squared over n. Okay? So immediately you see there's a problem. This was efficient in the sense that it was unbiased and it achieved the minimum variance possible. This one is not even unbiased. Okay? By doing this, you immediately introduce a bias term here. Now, what is true, though, it is asymptotically unbiased. In other words, if you have infinitely many data points, this guy goes away, then it's an unbiased estimate. Okay? But for a finite amount of data, it's biased. Also, the variance of a squared hat is 2a squared sigma squared over n plus 2 sigma to the 4th over n. Okay? Remember, we had this guy here, this variance bound. Now you have something very different. Okay, so this has now been lifted above the lower bound that you would have had before for the estimator they had. Okay, so this is not efficient anymore. Okay? Any questions? Okay, so what I'd like to do next is spend some time talking about an issue which has really become very popular in the last few years, maybe in the last 10 or 20 years, and that is estimating quantities for which you apparently need to know the underlying value of the parameters. So let me be more specific. We talked about mean squared error, right? Mean squared error is something that is not possible to measure unless you know the underlying value of the parameter, right? So if you want to design an estimator that somehow comes up with a small mean squared error, you're out of luck, right? Because you can't measure the mean squared error. So what I want to talk to you about next is a very clever trick for estimating the mean squared error. Okay? So what happens here is that you think of the mean squared error as a parameter that you don't know, and you estimate it. Okay? Seems a little counterintuitive, but it's a very, very clever idea, and it was invented. People have thought about this for a while, but the person who came up with this result his name was Stein, and he was a professor at Stanford in the 50s and 60s. Okay, and he's done some very, very famous things, this being only one of them. Okay, so the topic is estimating the mean squared error. And by the way, this is not in the book. Okay, so this is only in the lecture notes. And the way this is done is, the theory behind this, it's called Stein's Unbiased Risk Estimate, otherwise known as SURE, Stein's Unbiased Risk Estimate. Okay, and when we say risk, what we mean is mean squared error. Okay, in this context. In order to do that, we need to first prove a couple of simple results. Well, not so simple, but prove a couple of simpler results in order to get the final picture. Okay, so a very famous result is Stein's lemma. Lemma, 2 M's. I'm going to show it to you in one dimension, so in the scalar case first, and then I'll prove it in the scalar case, and then I'll show it to you in the general vector case. Okay, so this has to do simply with a Gaussian random variable. The result is the following. If you have a random variable z, which is distributed as a Gaussian with mean mu and variance sigma squared, okay, then the expected value of z minus mu times f of z is some differentiable function, basically any differentiable function, as long as it's well behaved. This expected value turns out to be equal to sigma squared times the expected value of f prime of z.
Okay. It's a completely unexpected and unintuitive result. Okay? And as simple as it is, and this is true for any differentiable f of z that satisfies, expected value of f prime of z is less than infinity. In other words, this right-hand side can't blow up. Okay. Now take a look at this result. Would you believe that this result was not known until like 1956? Okay, you look at this, and it must have been known since Gauss, right? But it wasn't. Okay, this guy Stein proved this result, and now it has found applications in all kinds of amazing places. So it's really worth looking at the proof to get some nice insights as to what's going on. Okay, so here's the proof. The first thing to do is to look at the right-hand side and write it down as an integral. So this is the integral, minus infinity to infinity, of f prime of z, p of z, dz. And what's p of z? P of z is just a Gaussian normal with mean mu and variance sigma squared. Okay? All right. Okay. So the next thing we do is we want to rewrite this integral in a slightly different way. And what we're going to do is something from high school calculus, or at least maybe some places high school, some places college. Okay, we're going to use integration by parts. Okay, just to remind you what integration by parts is, integral of u dv is equal to u times v minus integral of v du. Okay? Okay, so now we're going to define u to be p of z. We're going to define v to be f of z. Okay? So, now du is p prime z dz, and dv is f prime z dz. So now this right-hand side, this integral that we just had here, we're going to write it as follows. Integral minus infinity to infinity, f prime z dz dz. This is p of z, f of z, evaluated from minus infinity to infinity, minus the integral f of z, p prime z dz. Okay? All right, first of all, let's take a look at this. What is this function?
0.
0, right? Because you're kind of multiplying p of z, you're evaluating p of z at minus infinity and plus infinity, which we know just kind of dies out. So this part just goes away. Okay? So this is gone. Now what about this? So we need to deal with this guy. Now, what's true is that this p of z is a Gaussian, so we know how to calculate p prime of z. It's easy. P of z is 1 over square root of 2 pi sigma times the exponential minus 1 over 2 sigma squared z minus mu squared. Right? Okay, so if we differentiate this, p prime of z is 1 over square root of 2 pi sigma minus 2 z minus mu divided by 2 sigma squared exponential minus z minus mu squared divided by 2 sigma squared. Okay? And what's neat about this is when you differentiate a Gaussian, you get a Gaussian back. with something in front of it. So this becomes minus z minus mu divided by sigma squared p of z. Okay, so the derivative of p gives p back with this thing in front of it. And in fact, this is just the general property of the Gaussian. If you differentiate it a second time, you get a p of z again with a quadratic in front of it, and so on. Okay, these are called moment-generating polynomials. Okay, now what? So, now we're going to write this, this integral by plugging this p prime in here. Okay. So minus integral f of z p prime z dz minus integral z minus mu divided by sigma squared p of z f of z dz. Okay? And what is this? We can pull this sigma squared out. So 1 over sigma squared integral minus infinity to infinity z minus mu p of z f of z dz. Okay? If you look at this, this is nothing but the expected value of z minus mu times f of z. Right? So we're done. So this says the expected value of f prime of z is 1 over sigma squared times the expected value of z minus mu f of z. Okay, so put the sigma squared on the other side, the QED, you're done. Proof is over. Okay, so what did we use? Integration by parts. It's so simple. Okay, now a very similar version of this happens in multiple dimensions. So for a vector z, if z is not just a single scalar, then you have the z is, say, normal with mean mu and covariance c. Okay. Then it turns out this is the covariance of z with f of z. The covariance between z and f of z is equal to some matrix C, which is this covariance matrix, times the expected value of the gradient of f of z. Okay, that's this guy here. And let me just show you the scalar version so you kind of see how the two are related to each other. So here's the scalar version. Okay, this is the covariance between z minus mu and f of z. And this is the covariance, same thing. And the left-hand side, sigma squared, here's the covariance matrix, and here's the expected value of the derivative, this is the expected value of the gradient. They're quite similar. And we're not going to prove this. Okay, the scalar case is enough to actually bootstrap to the general multidimensional case. Okay, so this is what we needed so far. This is just sort of the setup, and now we're going to actually go after computing this Stein's unbiased risk estimator. Okay. So Stein's unbiased risk estimator. All right, so here's how we start. We have z, we're going to call it a Gaussian with mean theta and covariance c. We are going to estimate theta, okay, based on z. So we're going to get a theta hat of z, okay? So we can think of this as our data, okay, and this is the parameter we're going to go after. And what we want is to estimate the mean squared error for this theta, which is this expected value of the norm of theta minus theta hat squared. Okay? So this is what we want to get a handle on. See how we calculate it. Okay, so first, you define a function g of z as theta hat of z minus z. This is kind of a funny function to define. It's the difference between the parameter estimate and the data. Okay, and we're assuming these two things are the same dimensions in this case. Okay, so this function g is taking an n-dimensional vector and mapping it to another n-dimensional vector. Okay, so g is going from the n-dimensional Euclidean space to the n-dimensional Euclidean space. All right, so then next thing we do is we compute the gradient, or the derivative of this function as follows. So dij, we write this as dgi dzj. Okay? So what I want you to remember is that the function g actually looks like this, right? G of z is g1 of z through, let's say, gn of z. Okay? So this derivative is you're differentiating each one of these functions with respect to all the pieces of z. All right? So this becomes a big matrix. Okay? This is how we compute derivatives for multi-dimensional, in multiple dimensions. Okay, so the result is the following. The following quantity, r hat, which we call the estimate of risk, is the trace of c plus 2 times the trace of c times d, where d is this matrix, plus the norm of g of z squared. Okay? And when you compute this quantity, then the expected value of r hat turns out to be the mean squared error that you're looking for. So r hat is in fact an unbiased estimate of this mean squared error. Okay? Now let's take a look at this right-hand side. The mean squared error depends on theta, which is the truth, which you don't know. Right? Everything on the right-hand side of this, you know. You know the covariance matrix. You know d. D is just the derivative of these functions g. And g you know, right? It's just the difference between these. So this right-hand side, amazingly, does not depend on theta. Okay? So this can be used now in practice to estimate mean squared error. This can be very, very useful. For instance, suppose you've built an algorithm for estimating some parameter. And your algorithm, think of it as a black box, has a tuning parameter in it, right? Because, you know, I'm going to average this many data points or this many data points, or I'm going to smooth the data in this way or that way. And you can tune these parameters, right? Now, how should you tune them? Well, if you somehow knew the mean squared error exactly, well, of course, you would tune it to get the minimum mean squared error, right? But this gives you a way to do it. So you take your given data, using your given data, you compute this right-hand side with some set of tuning values. Then you can recompute this right-hand side with different tuning values until this guy becomes small. Okay? It's a very nice trick. It doesn't always work very well, but it's a very nice trick. And why should it not work very well? The reason is that what this shows you is that on average, this gives you the value of the mean squared error. What I have shown you says nothing about the variance of this estimate. Right? So in fact, the variance of r hat may be very large. So on average, you might get the right value for the mean squared error, but on any given experiment, you might not get a very good value for the mean squared error. Okay, so keep that in mind as well. Certainly, it's better than having nothing. Okay, so So I want to do this last part as well because I think it's very useful to have it as a sort of benchmark for the kinds of things that we've been doing. Okay, so I'm going to do it for the simple case. Where the covariance matrix is just sigma squared times identity. Okay, so let's write R hat again. This is the trace of C plus 2 times the trace of CD plus the norm of G of Z squared. This trace of C is sigma squared identity, so this is n sigma squared plus 2. The C, again, you plug that in here, becomes 2 sigma squared trace of D plus the norm of theta hat minus Z squared. Okay, I've just plugged in what G of Z is in here. Okay. Now let's take a look at the expected value of R hat. You get n sigma squared plus 2 sigma squared times the sum I equals 1 to n of the expected value of dii. Okay, plus the trace is the sum of the diagonal terms. I push the expected value inside the sum, and this is what I've got. And then the last piece is the sum I equals 1 to n expected value theta I hat minus zi squared. Okay? All right, so now I want to remind you is dii is dgi dzi. These are the diagonal terms of this matrix. I just defined it before. And we know that sigma squared times the expected value of dgi dzi is equal to the expected value of zi minus theta I times gi. This is just Stein's lemma that we showed you before. Okay? And now I can use this property to rewrite the expected value of R hat as n sigma squared plus 2 times the sum expected value of zi minus theta I gi plus the sum expected value theta I hat minus zi squared. Okay? So basically this part has been replaced with this part. Okay. Now where am I going with this? The last thing I really need to do is to note that this n times sigma squared is simply the expected value, it's the sum of the expected value of zi minus theta I squared. Okay? Now, how does this help me? I have 3 terms. This term, and this term. 2 of them are squared. 1 of them has a 2 in front of it and a product. Where do you think this will take me? Next thing I'm going to do is complete the squares. Right? This is like a squared plus b squared plus 2ab. Okay, so the next step is simply to complete the squares. What you get is expected value of R hat. It's the sum I equals 1 to n e ci minus theta I plus theta I hat minus zi squared. Okay? Now, something very cool happens. This cancels that. Okay? And then this becomes sum I equals 1 to n expected value theta I hat minus theta I squared, which is nothing but transform of theta hat minus theta squared, which is the mean squared error. Okay?
Wait, how did the squaring of the expectation value go inside?
It's like this.
Oh.
Okay, so the bottom line is this function on average gives you the mean squared error, and this was the proof. Okay, so it's useful for practical purposes. And as I said, the sort of prototypical example of this is you have x of n, a bunch of data, some collection of data, and this is going into your algorithm, which is your estimation algorithm, and out pops theta hat. And here, usually, you have some tuning parameters. Okay? What this could be is that maybe this is a whole family of algorithms. Okay? Maybe it's just not just one algorithm, it's a whole family of algorithms that's parameterized by some thing that you can just adjust. Okay? So, how do you adjust these? Well, you can take this data and put it through Stein's unbiased risk estimator. This gives you an estimate of the mean squared error that you would get with a particular set of parameters, and then you use that to change the parameters. Okay? And then you would select the estimator that is perhaps the most attractive in terms of mean squared error. Okay? Any questions? So just to give you a little heads up, next week we're going to do two things. One of them is, well, the Tuesday lecture we will cover some new estimation material, and on the Thursday lecture I will do a review and I will solve some example problems for the midterm. The lecture that we will have next Tuesday, which will be new material, won't be included in the midterm. So basically everything up to this moment, from the beginning of the lecture course to this moment, is going to be included on the midterm. The way the midterm works, and I'll say more about this next week as well, is you'll have the whole class, an hour and 45 minutes. It'll be typically 5 problems, and you will be allowed to bring in one sheet of paper, this size, and you can write whatever you want on it. And aside from that, you don't need any calculators, notebooks, or any other kind of aid is allowed. Okay? So that's it. See you next week. No, it isn't the only method. This is just one way to find it.
But it's a good way to find if we can reach the lower bound or not. If we cannot do that with that equation, then we cannot say that there is no other way to do that.
Oh, that's right. No, you see what you're saying is there's a sort of if and only if statement,
Yeah.
right?
Yeah.
So what this says is that if you can't show that it can be written this way, if you can show that it cannot be written this way, then there does not exist an efficient estimate. Okay? But often what happens is the situation is so complex that you won't be able to decide whether it can be written in this way or not. So you won't be able to use that reverse to disprove that one doesn't exist.
Yes.
You see what I mean? The theorem is most useful in the forward direction. Is when you can in fact do that factorization and get your minimum variance unbiased estimator.
Yes.
Yeah. Otherwise, it's not of great practical use to try to do it the other way.
Also, another question.
Uh-huh.
Then, can I see this?
Yeah. You know which one?
Here, before this one. Is it after or before?
This is first and then second and so on.
From this equation,
Mhm.
you said that we can write this form.
Right.
I have a question. If this is true for all of the values of I, can we prove that this is true?
No, that's not true, because this statement is only about the diagonal elements of this
Yeah,
guy.
I know.
Right.
So this could not be the Cramer-Rao lower band, and the Cramer-Rao lower band should be a stronger condition from this.
No, because if you look at this, what I'm saying is that this is the natural way to write the Cramer-Rao lower bound for that particular element, right?
I mean that this is the Cramer-Rao lower band.
Mhm.
So we can derive this from this.
That's right, but you can't go backwards.
We cannot go backwards.
Right.
So I mean that this is a very strong.
This is a very strong condition, that's right. Yeah, and
But this is not so strong.
right, so
this would not be-
follow, yeah. When I wrote CRLB, what I mean here is that this is the easiest thing that you can call the Cramer-Rao band for this case,
Yes.
right? It's not, often what happens actually is people make the mistake of completely ignoring this and writing that down and thinking that that's the Cramer-Rao band, and that's really not the Cramer-Rao lower band.
Yeah.
Okay, so oftentimes it turns out that computing this inverse is actually very, very difficult to do.
I know.
So-
My question is that is this equation, is this relation the Cramer-Rao lower band?
That's what it's called for the.
But it is not.
Yeah, I mean, if you want, this is what is called the scalar version of the Cramer-Rao lower bound for this general vector case. Now, you're arguing that there should be a more tight version of this, and I agree with you. You can write a tight version. In fact, the discussion is more general, in the sense that the Cramer-Rao lower bound itself is not necessarily always the best bound, right? There are many other kinds of bounds that tend to be tighter,
Yes.
right? So, you know, you may come up with a Cramer-Rao lower bound, and then you may show that nothing achieves it, right? And then you may be kind of discouraged. But what you've done is probably come up with a bound that is very loose. It's very conservative,
Yes.
right? There are other things, like there's something called a Barankin bound, there's something called a Zivzakai bound. There's a whole, decades of research that have been done into all kinds of different bounds that you can calculate. This is one of the things that is easiest to understand, easiest to teach, and easiest to use, which is why we use it so often. But you should not stop at Cramer-Rao lower bound. If you have a really interesting problem, this should not be the only place you stop. Definitely think about other types of bounds.
Okay.
All right.
So from an algebraic point of view, if we have a matrix that is positive definite,
Right.
and then if all of the diagonal elements of that matrix is greater than, for example, greater than 0, can we say?
No, you
Okay,
can't. Yeah, positive definiteness is actually a very tricky thing, because you can have a matrix that has positive diagonal elements, like variance, but off-diagonal elements can be negative.
Yes.
Still positive definite. I mean, the covariance is a perfect example, right? Because you can have variances along the diagonal and covariances, many of which might be negative.
Yes.
So you don't have to have all positive elements in order to have a covariance matrix.
That is the same problem as here.
Kind of the same problem, yeah. What's interesting, though, is that you can see that also in the definition of the Cramer-Rao bound. So if you look at this, of course, along the diagonal, you see that this term can be written as the expected value of the first derivative squared. with respect to I, you know,
Yes.
right?
Yes.
Which means that it's always positive. But in the off-diagonal terms, you always have to write it like this,
Yes.
right? There's no square way of writing this one, which means that it can be negative as well. So, okay.
Okay, thank
Good.
you.
Yeah, sure. Oh, you didn't take it, huh?